Hello, my name is Nicholas Kasanovic, and this is the supplementary video presentation for our research entitled Introducing Hand, Hyper-Resilient, Four-Fingered, Nimble, Dexterous Anthropomorphic Robot Hand Optimized for Research. A complete video presentation will be available upon publication. Grasping remains an open problem in general-purpose robotic manipulation. Many roboticists aim to use anthropomorphic grippers to utilize human intuition and grasp universality to enable complex manipulation tasks. Unfortunately, high forces present in contact-rich manipulation tasks can often damage robotic grippers. This is especially perilous for many popular robotic hands, which are expensive, fragile, and typically unrepairable by the end user. These additional hurdles can deter important contact-rich manipulation research from being conducted. Thus, we aim to alleviate such troubles by producing a customizable, inexpensive, and hyper-repairable multi-fingered robot hand optimized for research. In the past, we developed a 3D printed direct drive robotic hand named the Highly Dexterous Humanoid Manipulator, or HDHM for short. It was built in direct response to frustrations had with the Allegrohand, specifically in its kinematics and lack of user repairability. As such, the HDHM is composed entirely of commercial, off-the-shelf DYNAMIXEL actuators and custom 3D printed parts. Moreover, it features additional degrees of freedom that permit superhuman movements, such as finger roll. Similarly, other researchers developed the Leap Hand, another 3D printed DYNAMIXEL robot hand. Despite the success of both robots presented here, they are not perfect. For instance, we learned several lessons about the HDHM's inadequacies when deploying the robot hand for extensive telepresence research, leading to its usage in the $10 million ANA Avatar X Prize Finals, a worldwide telepresence robotics competition. These lessons were: 1. Fast-paced environments need rapidly repairable hardware. During the X Prize Finals, we broke the HDHM daily. Despite its modular construction, the lack of repair optimization led to maintenance taking up to 30 minutes of invaluable competition time. Hence, repair times must be minimized. 2. In telepresence, inhuman degrees of freedom are unnecessary. Most of the backlash from the HDHM came from the finger roll joint. Human hands do not have this extra degree of freedom. As such, telepresence-based control seldom uses this actuator. If anything, this extra joint increased unpredictable compliance, ultimately frustrating end users more than helping them. 3. Compactness can be more important for manipulation than rigidity can. The additional strength provided by extra thick 3D printed fingers is insignificant to the additional hassle it created when trying to grasp functional objects like cordless drills. 4. All robot hands break, but not all can be repaired. If there's any reason to use a custom robot hand over an industrial-grade gripper, it's the user's freedom to modify the hardware themselves. Hence, the hand must be optimized to emphasize modification and repair. Here, you can see the new kinematic structure of the robotic hand. The index, middle, and ring fingers share a biomimetic configuration. Contrarily, the thumb uses a different layout to approximate human hand motions with fewer joints. A special feature of the hand is this modular thumb. If the current thumb's kinematics are inadequate, another thumb with a different joint layout can be installed without needing to redesign the entire hand. To simplify assembly and repair efforts, the hand's design emphasizes standardized linkages that can be mass 3D printed quickly while adhering to auxiliary constraints. The CAD rendering of the hand, shown on the right, highlights each unique component with its own color. The large number of red and green components indicate significant reuse of parts in the hand. Joint optimization is demonstrated by our custom linkage backplate. This part replaces the DYNAMIXEL Actuators backplate and embeds ball bearings into each joint, improves airflows to the motors, and lowers actuator thickness. Also, this part enables several joints to be snap-fit together, further simplifying assembly. Nonetheless, the most noteworthy joint optimization technique employed was introducing sacrificial rotors to every joint on the hand. Doing this embedded a predictable and reliable point of failure for the robot. The vulnerability injected into the sacrificial part was a small radius fillet placed on the outside of the motor shaft coupler. A stress concentration forms along this fillet when excessive torques are applied to the coupler, leading to the coupler shearing off of the rotor, effectively disconnecting the actuator from the hand mechanically. Beyond purely mechanical improvements, we also present an improved telepresence control framework. This allows a human operator wearing Manus Quantum metagloves to control the fingers of the robot's hand in real time over Wi-Fi. Manus Core samples the data gloves to digitally recreate the operator's hand skeleton in Unity. Then, an inverse kinematics solver named BioIK retargets the skeleton motions to a URDF of the robot. Then, Unity sends robot joint angles over TCP/IP to ROS running on the Motion PC. Finally, the Motion PC uses the joint angle data in our own custom low-level hand software driver to move the physical robot. Now, onto our experiments. For our telepresence experiment, a human operator wearing the Manus gloves is commanded to quickly open and close their hands a total of 20 times. The hand attempts to imitate the operator's hand pose in real time. Notice how the hand barely lags behind the operator's movements. 5 separate trials were done, yielding 100 rapid large movements being recorded. Next, in our payload experiment, we fixed the hand to a robot arm and commanded the hand-arm system to grab a bucket with a pre-programmed power grasp. The arm then lifts the bucket and after 15 seconds sets it back down. If the hand supports the bucket's weight without breaking, the trial is considered a success. If it fails to hold the bucket's weight, or if a part mechanically fails, the trial is considered a failure. If the actuators of the hand fail electrically, the trial is given a special distinction. We started with a 3 kilogram mass and incrementally increased the payload until the hand failed 3 out of 5 trials for a given bucket's mass. If the hand got mechanically damaged during a trial, an experienced user with spare sacrificial parts timed how long it took for themselves to repair the hand. Following repairs, the hand was immediately sent back to testing. As a bonus for viewers of this video, here is a short clip of the hand being manually used for general telepresence grasping. World peace. Wow. This is really heavy. Oh my. And the hand still works. Results from telepresence testing came from comparing the URDF hand's joint angles to the real robot's joint angles. Here's a sample plot of transient data for the index MCP joint. Correcting for error demonstrates a hardware latency of 80 milliseconds, which is the difference in time from the robot receiving a position command to arriving at that position. There was also latency in the retargeting system. By recording the human hand in Unity in slow motion, we found that URDF motion retargeting took 70 milliseconds on average. We can do the same for end-to-end latency. On average, a full motion is imitated within 250 milliseconds. Further analysis revealed that network latency was around 100 milliseconds. This concludes the telepresence experiment results. As for payload testing, the results are more straightforward. This table shows successes, mechanical failures, and electrical failures for all trials and all payloads tested. The hand was observed to safely lift payloads up to 4.5 kilograms without failing. With spare sacrificial rotors, the hand could be pushed to lift loads up to a maximum of 5.75 kilograms. Payload testing doubled as a way of gauging hardware repairability. Here's some sped-up footage of the hand repair process. Due to the optimized and standardized design of the links, the robot could rapidly be repaired on site. Every mechanical failure was linked back to the sacrificial rotor's coupler shearing off at the injected stress concentration, as desired. This led to 0 actuators being damaged, with an average repair only taking 4 minutes and 36 seconds to complete. In conclusion, the hand is a low-cost and ultra-repairable anthropomorphic robotic gripper optimized for telepresence and manipulation research. The unique addition of sacrificial parts to a robot hand protects the gripper from sustaining excessive damage when experiencing large forces. Also, the streamlined and modular construction yielded an average repair time under 5 minutes. Ultimately, the hand's finger speed, payload, and compact form factor make it a competitive alternative to commercial robot hands, even without considering its unmatched ability to be repaired quickly. Thus, the $500 hand demonstrates its usefulness for riskier research topics like telepresence or contact-rich manipulation. Thank you for watching.